Let's talk about the chain rule, which is everybody's favorite subject from Calculus 1, right? And now it's just going to get worse. Actually, it gets better because, oddly enough, in the multivariable setting, at least to me, the chain rule is a little bit more intuitive than it is in a single variable setting. To lead into why we need the chain rule, think about this problem. We have a rectangle, and the width of the rectangle is increasing, say at 1.5 centimeters per second. The length of the same rectangle is decreasing at a rate of 1 centimeter per second. How fast is the total area of the rectangle changing at the instant when the length and the width are 5 and 6 centimeters each? So here's how we break down the relationships in this problem. We know that area of a rectangle is length times width. So area depends on length and width, right? Well, not so fast, because length and width in this problem are changing, and so they depend on time. And so ultimately the area will depend on time, right? So far, so good. Now there's a reminder of the problem statement. Let's go down a level into rates of change. There's a phrase in this problem that says the width is increasing at 1.5 centimeters per second. That tells us the derivative, dw dt, is 1.5. Similarly, the phrase that the length is decreasing at 1 centimeter per second tells us that dl dt is -1. And then the main point of this whole problem is to answer the question, how fast is the area changing at a particular instant? Now, when you ask how fast is the area changing, you are asking for the rate of change of area with respect to time. Okay, so far so good. Or is it? Because we want dA over dt. However, we've never written down an equation that relates area to time. So how in the world do we get dA dt if we don't have an equation or a function directly tying area to time? Well, that's where the chain rule comes in. So generally speaking, we will be looking at functions that have 2 or more variables in them, and each of those variables in turn will be dependent on another. And in a situation like this, where here f depends on x and y depend on t, then ultimately x and y are the middlemen, right? It's really t that's the primary mover of f. And so we may want to examine the rate of change of f as it's influenced by rates of change in t, but we don't have a function that is f of t equals something something. So we have to break this down into the derivative information that we have available and assemble that derivative information in a useful way. So we identify the middlemen. Here they're x and y. We identify all the derivatives that we can come up with based on the equations and the relations that we already have. So here we have, generally speaking, f written as a function of x and y, like f of xy equals x squared plus y squared. And so there we would have the derivatives, which are the partial derivative of f with respect to x and y. We also have the relationships between x and y and t, and so each of those relationships would be able to produce the derivatives dx dt and dy dt. Now there's a reason I've colored them red and blue, because if we take products of these things and you pretend for a moment that you're looking at fractions, which you really aren't, but that's okay, we'll pretend, you can see the dx's and the dy's cancel out, if you want to think of it that way, and what's left is something that sort of kind of looks like df dt in a fractional sense. What we're looking at here is that we can create the contributions to the total change in f with respect to d, where that total is coming through 2 contributions, one through x and one through y. And that is how we assemble the chain rule. So our 2 contributions to the rate of change of f with respect to t coming through the middlemen are written as products of individual derivatives, which we can get right out of the problem. And since we have 2 contributions to the total, well, we add them up to get that total rate of change. And that is how we build the chain rule, given the relationships that are flying around in the problem. Quick change just to show you that it's not possible to just say this is the chain rule formula. You will have different chain rule formulas to assemble based on how many variables you have, how many intermittent dependencies there are, and what the names are. It's just not possible to be able to say this is the chain rule expression. The chain rule expression that you will need to assemble is going to depend on the name of the function, the number of intermediate variables, the number of final variables, and all of their names. And so you just have to learn how to assemble them. And here's sort of a strategy. In this rather generic case, we have a function z. It's defined initially in terms of three variables u, v, and w, but each of those are in turn defined through a variable or a parameter named s. So ultimately, z will depend on s, and we probably want to examine the rate of change of z with respect to s. So we identify the middlemen. Those are u, v, and w. Those are the variables that transmit the information between s and z. What derivatives do we have access to? Well, a whole bunch. From the original functional expression that would define z in terms of u, v, and w, we're going to have three first-order partial derivatives. From the equations or the functions that relate each of u, v, and w to s, we're going to have their individual derivatives with respect to s. But now we have the information that we need. So for each of the middlemen, you make a little product that puts together the terms containing that middleman variable. So for each of u, v, and w, we'll grab the pair of derivatives that involve those and make little products out of them. Here we now have the three contributions to dz ds as they go through each of the intermediate variables, and we add up those individual contributions to make the total. And now that is what we could say is the chain rule for this particular situation. And here's an example showing this in action where we'll look at a very simple function, a couple of easy relationships tying together the middlemen variables with the final variable t, and we'll ask for a rate of change of f with respect to t at a particular value of t. So here's the situation. We have a function f defined with variables x and y, but x and y in turn are defined by a variable t. So ultimately, the x and the y are just the middlemen connecting t to f. T can take on all real numbers. If you're not told otherwise, just go with it, or use whatever is obvious from the domains of the component functions here. And let's say that we want this derivative. We want to find out the rate of change of f with respect to t when t is pi, because if t is ultimately the driver behind f, the ultimate independent variable, then we might want to know the rate of change of f with respect to t. And t equals pi is just chosen because it sounds like a fun point, right? So what's the problem? Well, the problem is there isn't a function directly linking f to t. So we have to connect all of our information down through the level of the derivatives. So before we put our brain in a twist about what the chain rule formula for this might look like, let's just take an inventory of all the derivatives that we have available. Okay, so for example, since f is a function of of x and y, we have, pardon the little color mix up there, but we have partial derivatives of f with respect to x and y. So the partial with respect to x is 2x, and the partial with respect to y is 4y. Now, those are the derivatives we've gotten out of the original function. But we also have the parametric functions over there that tell you how x and y are constituted as functions of t, and there are derivatives that come out of those. So for example, we have a derivative of x with respect to t. Coming out of the top of the two, the derivative of sine is cosine. And we also have a derivative of y with respect to t coming out of the t minus 1, and that's just 1. So those are the derivatives that we have available out of the original function and the two constituent functions there. And now, if you take a look at the derivatives that we have available, the reason I've color-coded them here is that if we take them as a pair and form products, just symbolically like that, If you pretend for a second that these are fractions, which they aren't, but we're all friends here, so we can pretend that for a moment, you can imagine the dx is canceling out, and what you see is that this produces a residual, a leftover, that's basically df dt. So this is the contribution to the total rate of change of f, or the partial of the total rate of change of f, which comes through the variable x. And if we put those two derivative expressions together, we have that product. Now we are kind of mixing and matching variables now, because now we have t's and x's in the mix at the same time in this derivative expression, and ultimately we might not want that, but we'll go with it for now. If we do the same thing for the derivatives with respect to y, again, pretend that the dy's are canceling out. Don't tell anybody you're making that assumption, but just do it anyway. What's left is the contribution to df dt that's contributed through the variable y. The two derivative expressions just have a net product of 4y. And so since f is based on x and y, the contributions to the rate of change of f come through x and y, and we've determined what those contributions look like. And so the total chain rule expression that can be built would look like that, plus that. That's the formal chain rule expression. You may or may not want to go for that immediately at the start of the problem. Here you can kind of find your way to it by just doing inventory of all the derivatives you have available, and then start looking at the combinations of them that will produce good stuff. In that process, we've also identified what this term looks like. And so we have that derivative expression. Now that's the derivative expression that tells us the rate of change of f with respect to t for any x and y and t. Specifically, we want to know about what this value is when t is pi. So this is bad form, but I've kind of run out of room off the bottom of the page. I don't want to switch to a new page, so I'm going to squeeze it in over here. And I'm going to put in the information that's generated when t is pi. Now when t is pi, x is sine of pi, which is 0, as far as I remember, and y will be t minus 1, which is pi minus 1, like so. And so then, when t is pi, x is 0, y is pi minus 1, and now we can bring all these parts together to give us df dt when t is pi, and we will ask for 2x times the cosine of t. Well, that'll be 2 times 0 times the cosine of pi. Well, that's -1, but we don't care because we're multiplying it by 0. And then plus 4y, and at this instance, y is pi minus 1. And there, it's squeezed in at the very end. Tidy that up just a bit. And there's the final value that we were after.